Hey guys, this is Kerry, and in this video we're going to be doing the group quiz for Unit 10. So I hope this is a helpful review. Because of limits on technology, I'm not sure how to screencast my TI-83 emulator on my iPad. I'm going to be solving a lot of these problems in Desmos, but I'll try to emphasize how an equivalent solution will be possible with the TI-83 or TI-84. If you want more practice with the TI-83 or TI-84, you should watch the videos where I taught that material that are also on this channel. Alright, so solve the following system of equations. If necessary, round your answers to the nearest thousandth. Alright, so you might think to solve the system of equations, since we know what y is in terms of x, maybe use substitution. So you get 3 to the x power equals negative x plus 10. However, you should recognize that whenever you have an exponential function equivalent to a linear function, this is a transcendental equation, which means that it is unlikely we'll be able to solve it algebraically. So an algebraic solution in this case, and usually for this type of equation, actually fails. So the way that we can solve this problem is to actually solve it graphically. So you would use your TI-83 or TI-84 calculator. I'm going to be using my Desmos app on this calculator. So for Desmos, let's see. We've got 3 to the x power for one of our equations. It's y equals. Next up over here, we've got y equals negative x plus 10. Oops, I put minus 10. And the solution to a system of equations is the point of intersection. So it looks like our solution is this value right here. I'm not going to copy that over onto the worksheet, homework sheet. So hopefully you keep track of it here. All right. So we're done with problem number 1. Also, your solution should be the coordinates x comma y that were from the graph. And the reason why we find both x and y in this case is because when we're solving the system had y and x in it, so we need both variables. For which values of x rounded to the nearest hundredth will this equation be true? So notice that this is only an x equation. There are no y's in this equation, so when we solve it, we're only solving for x values. If we want to solve for x values from this equation looks pretty impossible to solve. I'm going to guess that it cannot be solved algebraically, and instead solve it graphically by graphing both parts of this equation, this yellow part and this green part, separately. And if we graph these separately, we should be able to find the solutions. So let's take a look at Desmos to do this as well. I might have to flip back and forth in order to remember these. So for the first one, we're going to be putting in an absolute value. So on your calculator, that's the wrong app. On your calculator, you'll be doing a second catalog abs, but here it looks like I have an absolute value button. And I keep forgetting my y equals. So y equals absolute value of x squared minus 9, close the absolute value, minus 3. That's a crazy cool graph. Nice. All right, next up, we're going to be graphing a log equation, and the one that we got on to graph was y equals log base 3 of x. So real important, this came up in class today. In order to graph log base 3 of x, the way you put that in your TI-83 is to do log of x divided by log of the base. It's the same way we always put logs into our TI-83 calculator. Let's see how we can do that on Desmos. So there's another way you can do this on Desmos, but I'm going to stick with the TI-83 version. So we'll do functions miscellaneous log of x divided by log of 3. All right, so we've got our two functions here, and it's being shown on a similar window to what you would see on your TI-83. So if you do it on a TI-83, it should look like this. It appears that we have 2 points of intersection here and here. So in our equation, we wanted to only find the x values, so it looks like 2.29 and 3.63. All right, that's answer choice number 1. Perfect. All right, for problem number 3, the populations of 2 small towns at the beginning of 2018 and their annual population growth rates are shown in the table below. Assuming non-continuous exponential growth, so we won't have e in our equation, we'll be using the older version of exponential growth that we learned earlier. Approximately how many years after the beginning of 2018 will it take for the populations to be equal? So let's make a Jonestown equation. The equation for Jonestown is 1240 times 1.06 to the t power. Let's make a Williamstown equation. That's 890 times 1.11 to the t power. Now the challenge with this problem is that if you graph it normally, the values are too large to appear on the screen. So we're really concerned about our window. So let's set up our window the same way that we would, as though we would have a TI-83. All right, so this one is a little bit tricky, and it emphasizes an important idea with the window, is that you might have to make revisions to your guesses. So in terms of x-min, x is not a variable from either of our equations. So x really refers to the t value here. So if we're looking at time values, it looks like the range of possible values is somewhere between 7 and 125 for them to be equal. So I might at first look between 0 and 130. X scale is always going to be 1 for you guys on your TI-83 or TI-84. For the y scale, well, there is no y in our equation. The y scale is going to be the two populations. So it looks like since these populations already start at 890 to 1240, maybe we say the minimum population we'd be looking at is 0. I like to start at 0 when I have like positive quantities because it helps me to contextualize it. And then y max might be, I don't know, let's say 20,000. Maybe the populations get really large. So, and then y scale will be 1. All right, so I'm going to try to graph these on Desmos and see if I can mimic the process of revising the window the same way you would on the TI-83. So we're going to flip back and forth a lot here. So TI-83, let's see, you put in your two equations, y equals, what are the numbers? 1240 times 1.06 to the x power. And then over here you'd have your second equation, y equals, it's 800 something, 890 times 1.11 to the x power. And just like we said, the values are so large, they don't appear on the screen. So to set the window here, I'll be using this, and it's very similar to what you did before. So let's see, I'll take away the minor grid lines. I'm going to go from 0 to, I think we said it was 130. Yep, x-min is 130, so I'll go from 0 to 130. It looks a little different than your calculator, but I think you'll still find this useful. 0 to 130. And then the y-axis values were from 0, not 1, from 0 to 20,000, I think. And the step size, that's kind of like the x scale. So for you guys, it would be 1 here, but I'm just going to leave it like this. So when I graph it like this, it actually is pretty good, and I can see the point of intersection. But I anticipate that many of you, when you graphed it like this, you actually got a much worse graph than the one I'm seeing right now. So it looks like we need to really zoom in on the region where the point of intersection is. So the first thing to notice is we're actually showing a little too much of the x-axis. We don't have any x values, and I wish I could draw on the screen. We don't have any x values that are bigger than 60. So maybe what I'll do is I'll chop down the window, so instead of going from 0 to 130, it goes from 0 to, I think it was just 30. All right, so let me do that. And then for the y values, it looks like the intersection point is below 5,000. So maybe I'll adjust that window as well so that we have the y value, instead of going up to 20,000, just going up to 5,000. And that should create a more focused window that allows us to see really the specifics here. So x-axis is going from 0 to 30 instead, and y-axis is going from 0 to 5,000 instead. And if you graph this window on your TI-83, it's much clearer. Mine was clear in both cases with Desmos because it's a really great piece of software. But you, if with the TI-83, you probably didn't see it last time. Now the point of intersection is really clear. So you're going to do your second calc trace to find it. I can just press it. So 7.195. So it looks like that's going to be the answer for this problem. Again, I'm not going to show this on the sheet, so hopefully you're paying attention. So continuing on. Oh wait, actually, well, one last thing is, you'll see that here, we didn't get the window right the first time. And that's okay. The window is usually a process where you have to take multiple tries, zooming in on different parts of the graph to find the features that you're most interested in. All right, next up, what is the total number of points of intersection of the graphs, points of intersection of the graphs of the equations? This. So actually, we went over this one in class. We are good. We are not going to go over it now. Number 5, algebraically determine the solutions to the system of equations below. All right, so this is definitely a situation where we want to use substitution. But substitution we cannot do right away. We need to solve for x or y, so we're going to take the second equation. We do 3x plus y equals negative 3. Subtract 3x from both sides. That gives us y equals negative 3x minus 3. Substitute this in for y in the other equation. That gives us x minus 2 squared plus negative 3x minus 3, and not squared yet, plus 4, all squared, equals 25. This is a significantly better equation than either one we started with because it only has one variable, x. Next up, we need to simplify and distribute. So I'm going to take both those steps at the same time. I get x minus 2 times x minus 2 at the same time, sorry. This one here, we simplify what's in the parentheses by combining like terms. That gives us negative 3x plus 1 times itself because it was squared. And that all equals 25. Now distributing out here, I could distribute really slowly, but I can just distribute pretty fast, so I'm just going to write down some simplifications along the way, and hopefully if you aren't clear on where these came from, you do the distribution in detail. Next up, we combine like terms, giving us 10x squared minus 10x plus 5 equals 25. And at this point, we are hearing alarm bells, but at the same time, sort of seeing where the trajectory of this problem is taking us. We have x squared and x, meaning that we'd like to use some product. Perhaps the alarm bells that we're feeling have to do with this 10 here. Usually we want to have a value of 1 there or no coefficient. So before we address that 10, let's put it in the form that we need it to be in to use sum and product factoring to solve it. We need it to be equal to 0. So we get 10x squared minus 10x minus 20 equals 0. And we're really lucky. This problem that we have with the 10 takes care of itself. Every term on this side is divisible by 10, so we divide by 10 on both sides. That gives us x squared minus x minus 2 equals 0. Perfectly ready for sum and product factoring. You could put the minus 1 there if that helps you see it. Looks like our factors are going to be x minus 2 times x plus 1. And our solutions to this equation will be x equals 2 and x equals negative 1. Lastly, we also need to find y. My preference is to use this equation here to find y because y has already been isolated. So using this equation, I see that y is equal to negative 9 if I plug in x equals 2. And if we plug in negative 1 here, we get y is equal to 0. So we have our two solutions, 2 comma negative 9 and negative 1 comma 0. Next up, we've got a system of equations that we're going to be solving algebraically. So this one is actually better suited for elimination. And once you realize that, I think it's an easier problem to solve than the one I'm about to do. So I'm going to let you solve this one on your own, and I'm going to go over problem 7 in detail because that's a system of 3 equations. This will also be illustrating how the elimination method works, so I should help you with the problem before if you struggled with that. For elimination with 3 variables, we need one of our columns to completely match. The best choice in this case is y, because it almost matches, or it's easy to make it match. So we'll multiply this equation by 2 and this equation by 2, and that gives us a wonderful pattern where we'll have all 2's on the y column. Let's rewrite our system. So the first equation stays the same. The next equation becomes 4x plus 2y plus 6z equals 10. The next equation becomes 6x minus 2y minus 4z equals negative 26. And at this point, you want to pause for a second and make sure you didn't make any mistakes. I have made a mistake. If you make a mistake at this stage, you'll get the rest of the problem wrong, and it'll be really frustrating. Make sure that you distribute to all the terms. So the mistake I made was I missed one. It should have been 8's. All right, now that we've fixed that, I think we're ready to pair things up and eliminate the y values. So to pair things up, we've got 3 equations. Let's start by pairing 1 and 3. So when we pair 1 and 3, let me do this in a different color, pink here. When we pair 1 and 3, we get x plus 2y plus z equals negative 2. Let me just confirm again. Still correct. For the third equation, we don't want to be using the old third equation because we have a better new one. 6x minus 2y minus 8z equals negative 26. Adding these two equations together creates 7x minus 7z equals negative 28. Great. Next up over here, we're going to be pairing up equation 2 and 3. So for equations 2 and 3, we're not going to be using the old versions, we'll be using our two new better versions. So we'll use 4x plus 2y plus 6z equals 10, and 6x minus 2y minus 8z equals negative 26. When we pair these up, we'll add it column by column, giving us 10x cancels out, minus 2z equals negative 16. Pause for a moment and check your equations, because if you messed up here, you're going to be really frustrated with yourself, similar to before. Now, if you're watching this video and you're not a student of mine, you might see some shortcuts here. In fact, you might be a student of mine and seeing some shortcuts here. But I want to cover this video in a way that's most reminiscent of how it was covered in class. So I'm going to be using these equations as they are. So let's take our two new equations, which are already better than our originals because they just have x and z with no y's. So we're down to 2 variables from 3 originally. So we pair these two equations up. 7x minus 7z equals negative 28. 10x minus 2z equals negative 16. So in order to eliminate one of these variables, we need a column to match as well. You can pick either one. In this case, I think picking z is the easiest choice. So to make these match, let's multiply the first equation by negative 2 and the other equation by 7. Let's see what happens. So this will give us negative 14x plus 14z equals 56. 70x minus 14z equals negative 112. Adding these two equations, ooh, that doesn't cancel out, sorry. That gives us 56x. These cancel out, it equals negative 56. We divide by 56 on both sides, we get x is equal to negative 1. Finally, like a sign that we're doing the problem right. Because we got an integer value here, it feels good. Let's see if we can find out what y or z are. So we'll take this equation here. Because we know x equals negative 1, we can take that value, plug it in for x in this equation. That becomes 10 times negative 1 minus 2 times z equals negative 16. Negative 10 minus 2z equals negative 16, plus 10 on both sides. Negative 2z is equal to negative 6. Divide by negative 2, divide by negative 2. Z equals 3. Now that we know x and z, we are ready to solve for y. So I'm running out of colors for this problem here. Hopefully it's still legible despite the colors, but I think it's actually probably clearer that I'm using these colors. Each color represents a new part to the problem. X equals negative 1 and z equals 3. I'm going to use this first equation here. With x being negative 1, we've got negative 1 plus 2y plus 3 instead of z, because they're equivalent, equals negative 2. This gives us 2 plus 2y equals negative 2 when we combine these two like terms. Minus 2 minus 2, 2y is equal to negative 4. Divide by 2 on both sides, we get y is equal to negative 2. So our solution set for the problem is, our solution for the problem is the 3 values right here. X equals negative 1, y equals negative 2, z equals 3. For problem number 8, I will not be going over this problem in this video. I go over a very similar problem in the video where I teach about regressions. If you're struggling with this problem, I strongly recommend that you watch it, because a problem like this is going to be on your test. Now, the most important thing to check with these problems before I end this video is which type of regression you're using, because depending on which type of regression, you'll be using a different function in your calculator. So remember that all of the regression fits are under the, I'm not sure what menu they're under, because I don't have a T83 in front of me, but it's on the list button. I think it's actually second list, which is stat. And then when you go into that, you can calculate a regression fit. That's what it is, I'm pretty sure. I say it in another video if you want to see. But when you do an exponential regression, you want to make sure you're using the exponential regression option. We've looked a couple times at logarithmic regressions, which use the ln prefix, not the one we want in this one. We've also looked at linear regressions, which use the form y equals mx plus b, also not the one we want in this case. You may want one of these 3 on your test, and it might not be exponential. It might be exponential. So hopefully you figure out which one you need, because otherwise you'll be getting the problem incorrect. All right, see you guys in class tomorrow. Best of luck. Hope you were successful in this problem set.